Welcome back to Remote Trigonometry from Seacoast High School. I'm Eric Fearing, my pronouns are he, him, his, and most of my students call me Mr. Today we're working on Competency 1 Benchmark 8, the final benchmark in our unit on right triangles, and it specifically says we're going to use the inverse, sine, cosine, and tangent functions to solve for missing angles in right triangles. In our last video, we talked about taking a known angle and using it to find the length of a side in a specific triangle when we knew one of the other sides. It lets us take that ratio that talks about the shape of a triangle and scale up or scale down to an appropriate size to find the size of a similar figure. Today, we're going to take the information about shape in the form of two side lengths, that ratio, and work backwards to get the missing angle. I want to talk for a moment about what that aspect ratio means. So think for a second about the difference between a widescreen monitor and a traditional standard definition screen. What's the difference? Well, the shape, sort of obviously. The ratio is always 16:9 for a widescreen, and it's always 4:3 for the traditional screen. So one way we can express this is that 16:9 or 4:3 ratio itself. But that gives us the same information that some of the angles would. If we drew a diagonal in each of these rectangles, we would get two different angles. We have theta for the widescreen, and we have theta for the traditional screen. And those would not be equal to each other. Theta W is going to be a smaller angle. You can just sort of see it that way. What we're going to do today is take the known sides and work back to what that angle is, very similarly to how we could have used a known angle and one of the trig functions using that angle and one of these sides to find the other one. We know it would work for any multiple of the sides of this rectangle, and now we're just going to work backwards and go from the ratio of the sides to the angle itself. So here, I know this angle, the hypotenuse would be the diagonal of the rectangle. 9 is opposite, and 16 is adjacent to my angle. So I know the opposite and adjacent sides. That means I can say for sure that the tangent of theta W is 9/16. I could write a very similar equation for the standard screen. The tangent of theta is 3/4. So that gives us the same information of saying widescreen versus non-widescreen. If we want to find the angle, we just need one more step, and that's where the trig is involved. We're using an inverse function. Instead of having a degree as our input and a ratio as our output, we're going to switch those. We're going to say that the angle, theta W, is equal to the tangent inverse, which is written with a little -1 superscript that looks like an exponent, but it comes between the 3-digit abbreviation and the input there. So we would read this as theta W equals the tangent inverse, or the inverse tangent, of 9/16. And to find that number, we just need to go to a calculator. So this is desmos.com/scientific. We have the sine, cosine, and tangent buttons just there on the left-hand side. To get the inverses, we hit function, which will cause our whole keypad to shift. We still have sine, cosine, and tangent on the left-hand side. We need the tangent inverse to do what we're about to do. Then we're going to switch back to a keypad and type in 9/16. And now if we're in degree mode, which I think I talked about last time, we'll get the right answer right here. Theta widescreen is approximately 29.4 degrees. Now, if we want to do the same thing for the standard definition television aspect ratio, we would just do it with 3/4. We could say that the tangent inverse of 3/4 will give us our unknown angle measurement, and we do that just as easily on the calculator. Tangent inverse, clear it out first. Tangent inverse of 3/4 is 36.9 degrees. So sure enough, this is a larger angle than this one was. That makes sense. Visually, it's no problem. We get a much skinnier screen. As a rectangle, we get a less tall triangle. So the angle isn't as steep. And here's the steep one. So in the homework, you're not only going to be doing tangents, you're also going to be doing the inverse sine and inverse cosine functions. So the one additional step is you're going to have to choose which ratio it is. Obviously, I can't do that for you there for every problem. But let's do a couple of examples. So here's our right triangle, right angle on the bottom left, labeled ABC, with theta marking the angle on the top. And we're being told 3 and 5.6 are these two sides. We don't know the third side, but we do know it's a right triangle. We could use Pythagorean theorem to find this, but that is just several extra steps we don't need. What we want to do is label the sides of this triangle in accordance with the angle that has been marked. So we want to find theta. We need to consider whether these are the opposite, adjacent, and hypotenuse according to theta. Hypotenuse, easy as always, across from the right angle. If you need a review on how to do this, I believe it's benchmark 2 is labeling the side opposite an angle and the leg adjacent to an angle. So now what we know is the hypotenuse and the adjacent leg. If you'd like to just check your poster, hypotenuse and adjacent appear in the cosine ratio. So we're going to say the cosine of theta is adjacent 3 over the hypotenuse 5.6. And today we're taking inverse functions. So to find theta, we do the inverse cosine of 3 over 5.6. No reason to make that fraction into a decimal early. Doesn't matter at all. We're just going to plug it into our calculator as the fraction to get as precise an answer as we can, and we're only going to round in the last step. So pulling the calculator up, we need the inverse cosine this time, which I'm still on, which is nice. And now I can just key in 3 divided by 5.6, and we see 57.6 degrees. I'm going to write degrees every time I set something equal to theta, just because I know an angle is supposed to be matching the degree unit. When we use a Greek letter, it's because we're using an angle. So I'm just going to try and keep track of that. When you put it into the Google form, obviously I'm not that worried about whether you include degree or not. You can type it in. If you remember to, it's a good plan. All right, and we'll do one more. So now you've seen a tangent and a cosine. So spoiler alert, we're going to do a sine example. B. We're going to have a 16 hypotenuse and a 14 opposite leg. And those are opposite and hypotenuse relative to angle theta. This one's adjacent because the leg touches the angle. So I can say that the sine of theta is 14 over 16. Okay, I really want to reduce that right now to 7/8, even though it doesn't really make any difference because we're about to put it into a calculator anyhow. we can say that the inverse sine of 7/8 will give us our unknown angle. So the inverse sine, tap out. Remember, you can click back to main if you have a touch screen like an iPad, or if you just don't have a keypad to type it in quickly. 7/8. And it's already on our screen, 61 degrees. So theta rounds to 61.0 degrees. So there you've seen ways to find the missing angle using the inverse sine, the inverse cosine, and the inverse tangent functions. And that brings us to the end of our first competency, everything we needed to learn about right triangles. The next competency is about triangles in general. We're going to use the laws of sines and cosines. That are some formulas that let us find missing sides and angles in those. Coming up next. Thank you.